welcome. Thanks for coming along. Some confusion on the talk. So this is performance budgeting, swapped around talks from tomorrow. Who was in Ari's talk earlier? Oh, man, too many. He's really raised the bar too high. I've got no rock. If I say, what way do we do it? Oh, come on, once more. How do we do it? Yeah, go on. Just get a bit of that energy going. We've got another hour going before we can get to the mixer and everything like that. I'll try and keep the energy up, but it's quite a lot of technical stuff to go through. So I'm Steve Walker. Hi. I've been in the industry since the turn of the century. You can tell from the hairline. Backgrounds, physics programming, animation, IK, engine architecture, various things. And I've been in CTO and technical direction type roles for about the last 10 years. And I'm now technical director at Sony Firesprite. I'm coming at this from a fairly high level. I'll be starting with some overall thoughts on budgeting, and then a little bit later, we'll dig into some of the juicy details my team's been discovering moving to Unreal 5. A little bit about Firesprite, in case you don't know us. We had Horizon Call of the Mountain out last year. Went pretty well. Some awards and stuff. There's loads of great things we could talk about that development, loads of cool stuff we had to do there, but it's all UE4. You don't want to talk about that. You want to think about all that Unreal Engine 5 goodness. So since then, we've been looking at what our next title is, but I can't see anything else there. Getting ourselves going with UE5, doing various tech investigations, demos, pre-production, that kind of stuff. So I'll be pitching this talk really anyone in the team who's interested in making games that run at frame rate. We'll be looking at 2D flat screen rather than a VR focus. And I am coming at this from a console development standpoint and a AAA team standpoint. But I think what I'm saying is still useful for other platforms, smaller teams. You know, I've worked on all sizes of teams and platforms in my career, so I'll try and make it as relevant as I can. So, on to the budgeting. Are you a technical director? Are you being asked questions like these? What's my polycount budget for a tree, Steve? What's my GPU millisecond budget for hair, Steve? How many enemies can I have, Steve? So budgeting's always been a bit of a finger in the air estimate, but it's far better to have that finger in the air to work with than nothing at all. So before you deploy the finger in the air, let's have a little bit of history on how it's been done. So I'm talking now from my experience, PS 1, 2, 3, 4 eras, different people, different projects, etc. It may vary. There isn't a book on this as far as I know, so I'd be really interested to hear if you're working completely differently from me, especially if you've completely nailed it on how it works in your team. So GPU millisecond budgets, they've always been there. We've usually had a pretty good idea where our GPU's going, you know, milliseconds on each part for the rendering, and then it would lead to a polycount budget. Woo! Hey guys, we've checked it out. You can have X polys for a character, Y for an area of environment. Lovely. Off you go and build it. It'll probably be fine later when we put it in the game. CPU millisecond budgets. So these have been very important in the past. I've got the wrong version of the slides here somehow. I'm going to have to go and scroll the notes occasionally, sorry. CPU millisecond budgets, these have been very important. They might do something like physics object limits, raycast per frames, how many characters are active at once, that kind of thing. Obviously, it depends on your game requirement. Vehicles can be very expensive. PS 1, 2, 3, we were really squeezing the last drops out of that CPU to achieve what we wanted to in the game. So this is where I've got to do a bit of magic here. Just said all that. So then we have memory and disk space. So this has varied over the generation. Memory's always tight, but is it so tight you need to worry about it up front, maybe in pre-production? That's varied. Traditionally, textures would be a massive hitter here, and you'd probably end up limiting the memory textures for certain things would take up. On the disk space, storage medium changes, suddenly you have all the room in the world, and then the art changes, and you fill it all back up again. Whether that's, again, a big limitation for you, it depends where you are in that cycle of storage and art. Okay, so let's have a look what's changed. What's it like if you're asked to come up with a budget today as an Unreal Engine 5 console studio, like just happened to me? So GPU is still a key resource, but how we use that GPU has become more and more complex over time. Unreal 5 has all these amazing systems, so presuming you're using Nanite, hint, probably should, no more polycount budgets, woohoo! Nanite will take all those really high detail meshes you put in the game and automatically create a mesh for rendering with the detail you need it and where you don't need it and simplification in the places you don't need it. What that whole suite of Unreal 5 systems means is that a large chunk of your GPU is used by these base systems, and the cost is based on what you feed into them. It's no longer the case of just putting the rendering markers around a tree and going, oh, it takes X milliseconds, that's outside my budget. The true cost of that tree is a quite complex interplay of how that object's running in your system, how it's lit, what shadows it's casting, what shadows are casting on it, is it moving, etc., etc., etc. So context is everything. Unreal will do its level best to make sure everything runs well, and looking at anything in isolation outside the context it's used in can be misleading. CPUs. So CPUs have got better and better over time. Limits are higher. You will need to worry about the code in your ticks being well optimized, but is it something you need to concern yourself with in pre-production? Well, it's going to depend a lot on your game type and frame rate. The part of me that worked on those earlier consoles thinks we shouldn't ever have to worry about CPU anymore because we're comparatively rich. You know, CPUs these days can actually do a hell of a lot. So when you come to look at the feasibility on a game design, we should be able to achieve most things that design want from the CPU side, but we still manage to hit issues. It can still be difficult. What you want to do is identify early whether you need to be clever to achieve those things the design wants, or whether it's a relatively easy case for you. And then keeping track of where you are on CPU performance in development, well, all performance in development, and not saving issues for the last minute is frankly really good for your health and the health of your team. So there are some of the issues you may hit on CPU. For some games, maybe open world games with a hell of a lot going on, you might hit CPU issue from ticks, or maybe physics if there's some major physics simulation thing that you've been asked to do. On that side, the animations particularly have been an issue on the tick side, but we now have thread-safe animation and animation layers in Unreal 5, which you should check out. The other side, particularly on a 60 frame per second or more game, can be render thread, which might be high from rendering loads of objects. Although Epic are continually improving things, and looking at the slides earlier about the roadmap, hopefully to infinity and beyond is the direction. So, okay, memory. Matt talked about this a lot earlier, so I'm glad I'm not saying too much on memory in this talk. Really, a big thing to think about here is fixed costs. The majority of your memory, your console memory, will be used by fixed costs now. There are a lot of fixed costs just to running Unreal. All of those systems use their own memory for buffers, etc. But on the plus side, some of the big ways you would have run out of memory in the past are now in fixed-size streaming pools. So we've got the texture streaming pool, and now we've got the Nanite streaming geometry pool. So, you know, what you need to look at here is what you have left in your game that falls outside of these pools. So things like anim data, skeleton data, non-Nanite meshes, non-streaming textures. Look at what your game and leaves you with there, and see where you're at early, and then predict ahead whether that's going to be a big deal for you and a big problem. Again, most of this can be solved with coding. You're identifying whether you're going to really need to be very clever about how you stream certain things in, and the way you utilize that remaining memory that you've got outside of the fixed costs. Disk space. So, Nanite, super high detail models, super high detail textures. They're big, right? They're going to take up a lot of storage on your disk and in the package. But on the plus side, we have really great asset sharing now. If you're building an open world game or some other types of game, you may be using similar trees all over the place. You may be using bits of building to build up a larger area. It just may not be a problem for you. We're also now at the point where most multiplayer games will not put their full and best version on the disk. They'll put a smaller version on the disk, and then, as I'm sure you've experienced, you'll put the disk in and you'll get a massive package download and get the really high detail stuff in there. So single-player console games are generally sticking to the size of the disk still and wanting that best experience if someone plays completely offline. But whether this is going to be standard when you release, not sure. So you want to flag early if disk size is going to be an issue for you. It's likely to be, if you're single player, you have a lot of bespoke and unique environments and characters. Otherwise, keeping the package size down is a good thing anyway, but you might not have that hard limit. So there's no point putting assets in the game that are way more complex than we will ever see. There are some costs to running them in game, and obviously you grow the package size without needing to. So you want your art teams to be going for quality, but keeping the detail to the point where it's actually giving you something visibly in game. So things got more complex. Does that mean you're saying we can't do budgeting anymore? Well, not quite, but I am saying simple single number budgets are often no longer appropriate. Many of the ways we've been budgeting in the past, fixed polycounts, and even to some extent GPU millisecond counts, 2 milliseconds for lighting, 3 for characters, are no longer as useful as they were. And that's because context is key. The way you're using assets, lighting, engine features, all comes together to give you your cost. Unreal is always trying to run things as optimally as it can, caching things, culling things, scaling things. The true cost of something in your world is always varying depending on how successfully it's doing that. Or to put it another way, how successfully you've got out of the way and allowed it to do that. So when we're being asked these budgeting questions, perhaps during pre-production, what are we actually being asked? What do we need to know? And how do I help the team? When I've been putting my thoughts together for this talk, I've got it down to 3 questions to answer. What features should we choose for our game? How do we know what we're building will run? And how do we get the best out of the technology we have? Awesome as it is. Okay, question 1. By features, I'm covering back-of-the-box features like frame rate and resolution, Unreal Engine features we might choose to turn on or not, but also what design choices we make, what quality and type of assets we should be making for the game. When you come to think about a game, the game you want to make, there are 3 things you're looking at. So you're choosing your feature set based on those things. There's the design and the game type, and what are the things that sit well with that. There's a technology you're using, what's it good at, what are its limitations, and then the visual quality bar that you want to achieve. Your game wants to sit nicely in this triangle, fitting the bill on all these areas. Sometimes it feels like the corners are pulling away from each other, and there's a bit of a battle. But I've put design at the top of this triangle. I know many of us are coders, but I've put them up there for a reason. You should never do things for the sake of either your tech or your visuals that goes against what works for your game type or design or what the players of your genre really want. But sometimes, with the right team attitude, you can look at the design from different angles and find the version of the design that works best with other areas. You might want to ask, what do we want players to feel here? what are the different ways we could go about achieving that? If a team's working really well together, you can find things that play into all three, with technology supporting the game design and really helping towards a really high quality visual bar. It's always best to spend your performance budget on things that your game is about or that players of your genre will really care about. Oh, come back to that in a sec. So I did want to say here, 60 frames per second is still hard. It has been every generation. So I've got an informative graph of shiny stuff to illustrate that. It may be obvious to all of you here, but it's worth saying for anyone it's not. 60 frames a second means you've got 16 and a bit milliseconds for a frame. 30 frames a second means you've got twice that much. But actually, it's usually worse than that. There's a certain fixed cost to getting a frame drawn. So as you can see from the graph, 30 frames per second gives you a lot more shiny. It might give you around 3 times the GPU to do all the things you want to do graphically. I've put GPU milliseconds on there, but CPU main thread, render thread, the situation is very similar. This has always been the case, each console generation, and we always go, oh, every game's going to be 60 now, and this happens, and the quality goes up, and it's still very difficult to make that decision. Frame rate makes such a huge difference to your performance budget that it's the thing you need to think about first. If your creative director is saying, oh, we might like 60 frames per second, or oh, I'd kind of prefer if we did 60, you're probably wrong to be aiming at it. And at some point during dev, it makes such a big difference to those budgets that you'll probably end up at 30. You should have had this conversation earlier in really clear terms. And it will affect everyone: tech, art, cinematics, lighting. If the team is saying, this game must be cinematic 60, Steve, then that's the aim. And everything else you look at is framed around that. And frankly, quite a few compromises will have to be made to make it happen. But of course, 60 frames per second gives us 2 separate things: a smooth, solid feeling world and a sense of speed, and better responsiveness. Hang on one sec. Sorry, just trying to sort these notes out. So I've put these separately because I think we'll solve them separately. I'm going on a little tangent here. There's a lot of work going on right now on interpolation and intermediate frames. This is really exciting. When we're good at that, you'll be able to update it to lower frame rate and still get that solid feeling world and that sense of speed. Responsiveness is an interesting one too. The reason 60 frames per second works better, or one of the reasons it works better, or higher if you're a PC shooter, is not just the frame rate per se, but we lose frames in the pipeline. And at 60, those lost frames in the pipeline are shorter as well. So we may be able to look at the pipelines and work on that responsiveness separately from the frame rate question. Have a look at the low latency frame syncing mode and documentate in Unreal and the documentation there, just to make sure you're well aware what's happening in the pipeline. There's a CVAR for that. So input responsiveness and render latency are really important in lots of game types. And it's super subtle. Say in a driving game, you can test a higher and lower latency version next to each other, and players will go, oh yeah, I think it's the same, as the brain kind of corrects. But then you get subtle feedback like, driving isn't fun, or it's hard to drive, I'm crashing a lot. So if that's you, make sure you understand your pipeline, how your inputs code's working, and how your whole pipeline's working from stick movement to seeing it on the screen. Anyway, back to frame rate. Right now, you need to make that decision. God. Anyway, you need to make that 60 or 30 decision because it's the real key thing that you have for both input responsiveness and latency. Okay. The next big decision that frames everything else is resolution. We've got 4K screens now. We want native 4K. No, we probably don't. Certainly if you're choosing a single mode to run in rather than a lot of user options, upscaling is great, and it's getting better and better. Spend more on pixel quality at a lower resolution and then upscale. From our test, the quality you experience is more about temporal and spatial pixel stability and quality rather than resolution. So we should be asking, how much to upscale? You'll be looking at how to upscale all of the time and whether you want to variably change upscaling. It's great, again, to have this worked out early in production to frame the other performance decisions around. You can always tweak it a bit later, but again, it's going to make a massive difference to your GPU performance, so get an initial finger in the air of where you might sit on it early on. And involve creative in decision-making. I know I'd like to just decide everything myself, but when you're doing comparative tests between levels of upscaling, it can be great to get multiple people involved and a buy-in from your team. Make sure you review it in motion, because when the camera's stationary, the image will converge to a higher quality result. So if you just compare with screenshots, you're not going to get it. You need to have a moving scene in order to do those comparisons. And look at intermediate resolutions and dynamic upscaling. Okay. I think it's worth going over this diagram from the Unreal docs. We're using the system just like this. There are two upscales. We've got a primary resolution to render the geometry and do depth of field. Then temporal upscale, noted there as TAEU, but that should be TSR now. And then we've got this secondary resolution here that we're doing motion blur, bloom, and tone mapper at before a final spatial upscale to the final res to do all that nice crispy UI and actually output the game. So Unreal specifies these as percentages, which I find a bit confusing. So I think it's easier to understand if we work backwards through it. So I use the settings we're using as an example. Obviously, the settings you choose may be completely different depending on your use case and what your team agrees. So 4K, so we've got a 2160 vertical resolution for the back buffer. We're using 94% for the spatial upscale, 90% for the spatial upscale. So 90% of 2160 is 1944. We're then using 65% for the temporal upscale. And now that's 65% of the secondary resolution, not the final resolution. So 65% of 1944 gives us around 1263-ish. That can drop variably for us to around 1080 or maybe even lower if there's a hell of a lot going on, but hopefully not much lower than that. Although we will turn that off in development builds, as it's easier to spot and call out a frame rate drop than it is a resolution drop during development, especially when you're doing performance testing. This is the resolution we want to be running at. Let's get everything running at that the best we can, and then the rest-run variable is headroom for unexpected situations, etc. So there's the CVAR for controlling whether you're running variable or not. When that is set, screen percentage is no longer used, and we specify a min and max screen percentage as well. So note, having a high max screen percentage will use more memory for screen buffers, and there's a hell of a lot of buffers in there, so just be aware of the memory considerations there. We're getting pretty busy already with the CVARs here, but here's another little tip. We're using CSR. The results are great in our cases, but it can be expensive out of the box. Make sure to tweak the settings. We're finding the history buffer might not need to be super sampled. Doesn't make much odds for us. That's the CVARs we've ended up with to get you started. Okay. So we first answered that frame rate and upscaling questions. Then you can have a look at how you use Unreal and the asset quality you might choose. So with Unreal, we've got all these amazing systems at our disposal. Epic talk a lot about this tech being a toolbox, and some tech you might choose to use or not. So firstly, I think Nanite is brilliant. When you come and assess any system, there are pros and cons. But to me, Nanite's a no-brainer. So I'm going to presume you're using it, along with things like virtual shadow maps and the texture streaming pool. All of those tools are aiming to deliver quality and only spend where you need to and can afford it. Lumen is also awesome, but I won't presume it on a console game. We're using it. I know some other studios are not, particularly if you're at 60. The cost is reasonably high. But with the right settings and some compromises on the lighting you choose, it can be a good call even there, giving you beautiful out-of-the-box global illumination. You will need to work on settings reductions from the defaults for console, though, and that goes for 30 or 60. That lumen call is very much going to be dependent on your game design and where you sit in that triangle. Oh yeah. Everything does work great together. Coming into a game, my default position is to use the entire UE5 tech stack unless there's a good reason not to. You may hit those reasons. There are some other things like PGC that you may use or not. Where's that slide gone? So really a big choice you're going to have to make is how you're doing your lighting. Both global illumination and shadowing are expensive if you're going for a high frame rate. We've come from a generation or two where most games were using baked lightings. So our lighting environments have got used to lighting environments with lots and lots of lights around the place. If you go dynamic, you have to decide if those lights will be non-shadow casting or shadow casting. Non-shadow casting lights are very fast in UE5, but they're only really suitable for subtle lighting. Shadow casting lights can get expensive. You also have the option to use emissive textures to light, like we saw in the Matrix demo. These are very efficient and great for frame rate, but our findings are they aren't a fix-all yet at this generation. We'll use it for some light types, larger glowing surfaces maybe, but for others it has a lot of artifacts. At the settings we need to get it to run well for console. We just don't have enough rays there for consistency, particularly on smaller visible light sources. And it'll look great in a screenshot, but it won't in motion. You may be able to design your environments to work well with emissive for the performance benefit. For instance, hidden light sources can work really well with light like bleeding round a corner. But do you really want to go back to baking? Probably not. The workflow advantages alone are massive to go in dynamic. Having all the lights bake every time something changes was a real drag. And that's before you even get into all the massive advantages of the lighting properly affecting things, moving through the scene, and the quality bar advantages. I would always prefer dynamic. However, if you need a really complex lighting environment and you need a high frame rate, particularly if you're a VR title, you may need to carry on baking. So consider design options. Given the large advantages of using the whole UE tech stack, you should see if it's possible. A decision like, hey, actually, let's set this game in the day with a single light source could make it possible for you to use Lumen and a high frame rate target. It's the kind of thing I'm talking about when I say to look at the design from different angles to find things that fit in that triangle of supporting the design but working well with your tech and the high quality visual bar. Obviously, if that doesn't fit with your game, if you're making Batman, you're not going to set it in the day. But if it's a close decision. So we know our frame rate, our resolution to work at, the basic building blocks of Unreal Tech we might decide to use. Next, we need to work out how complex our game is and what our asset quality is going to be. And that's where we need to move on to question 2. How do we know what we're building will run? Okay. Test early, test often. What you're aiming to do is take tests on final hardware or lowest hardware if you're across many. Switch, Series S, looking at you guys at the back. And then take those results and turn them into something the whole team can understand and get on board with. You want to be testing as early as you can in pre-production with as representative as final assets as you can, and keep on top of tracking performance as you develop. This is a super important one. Make sure to test in your final lighting environment. Make sure not to make the mistake of testing performance on things in too simple a lighting environment. A lot of the cost of your asset will come from lighting them. For instance, in order to work out what character we can afford to run, we first need to know how it will be lit in the game. What's the worst case you might have of the number of lights, particularly shadow casting ones, hitting that character? And make sure to consider all the lights you need in the scene. For instance, I work with some amazing cinematics people, and what they like to do in cutscenes is a bit like the movies. As well as the lights in the environment, they like a rig of lights around the character in the scene to really make them look great and really want to make them pop. And I want to support that, right? So actually, that's a bit of an open question for the group, actually, for Unreal. Can we achieve those kind of character effects with reduced cost? Maybe those lights are only taking into account exactly what they need to. Anyway, consider earlier how you're going to be lighting the environments and the different lights you might have in the scene. So add on-off switches for features. Our costs are coming from an interplay of the features we turn on, the assets we add, and the underlying system. We can't just put a GPU scan or markers to really understand where the cost's going. For instance, if we see a total cost for shadowing, that's coming from the lights we have on, the things that casting shadows, the things receiving shadows, how well the cache is working, etc., etc. In order to really know how much, say, a character's hair is adding to the cost and all others, we need to be able to try it with and without. So have on-off switches and flexible code in terms of spawning lights, assets, and characters. This will help you measure the cost of adding more complexity to the scene really easily. So let's move on to an example test. Okay, got a picture. It's the problem of not being talking about the games we've just done. You don't get as many nice pictures. Here we have a dense jungle test scene that's been put together but not yet optimized. I think that's more useful to show you than something that's already at its best. Here we were aiming for 30 frames per second, and it's running on PS5. The stats you can see on screen are from Stat GPU. There's no characters on the screen, though there is a character in the world somewhere here. There's one main shadowcaster, the sun, and a few additional non-shadowcasting lights. The leaves are all moving with WPO, which you would see if I was brave enough to do a live demo. So you just imagine that, right? The leaves are blowing gently in the wind. It's beautiful. So that total, 31.69, is a useful top line to look at. If we were aiming at 60, wow, there's a long way to go. As it's 30, we are in our 33 millisecond budget, but there isn't much headroom for characters, VFX, complex lighting, the rest of the game. So we'll have a little look here how we might bring those costs down. First up, it's interesting to have a look at the big hitters. So we've got Nanite. TSR, we mentioned. We might want to have a little look at the settings, see if there's any more we can do there. Then lumen reflections. Though actually shadows between shadow depths and projections actually is a little higher than lumen. And that shadowing cost would go up with more lights. Going down hair strands, the character we can't see is running strands, and we're picking up a few costs. You could flag that as something you might want to look at. So we'll do a couple of those on-off tests now. We know that world position offset and alpha masking use the slower programmable rastering path for Nanite. So we're going to try comparing the GPU times for this view with those features on and off. So There's the default. Watch some of these leaves. These ones particularly. Mass geometry off. So our average total has gone down from 31.69 to 26.04. That's 5.6 milliseconds off. So a lot of that cost gone from nanite passes, particularly the visual buffer's gone down from 3.96 to 2.24. But a lot of other things have gone down too. Lumen reflections are down, shadows are down. You can start to see what I'm talking about with that more complex interplay of where costs come from these days. But obviously, we've lost the alpha on the leaves, and we've used alpha cutouts for our leaves, so it's visually affected the scene. So mass geometry back on, and now turn off WPO. Everything just stopped moving in my imaginary live demo. You've imagined that, right? Thank you, everybody. But now we're down. 31.6 down at the start to 23.99 now. That's 7.7 off in this scene. A chunk of that's nanite, but also a massive reduction in shadowing. With anything moving that casts shadows, or with moving shadow casting lights, the virtual shadow map pages need to be updated. I'd highly recommend that you put together this kind of test with the different lighting setups that you may find in your game, as that interplay of lights and motion is vital to your final costs in a scene. So if we turn them both off, that's 10 milliseconds off the original scene. So we can see they are big hits to our performance. So what can we gain from that? Well, here's our nanite performance order in order of preference. We can get some ideas about what renders slower and what renders faster, with static, non-moving geometry being the ideal case, and that animated foliage adds cost, particularly with static shadow casting lights. If we decide to add animated foliage to our game, we're going to have to be a bit careful, as it's continually invalidating the shadow cache. In our case, we choose to specify much tighter limits on lighting where that kind of animated foliage is in use. So a couple of specific outcomes from this test that we took from our team. What you might take might be different depending on your design and aims. So we explicitly disabled alpha testing in shadow passes to gain back performance. This is an engine change we currently have at 5.4. It may not be relevant later as Epic are continually evolving. So we changed the engine to just disable alpha testing in shadow passes. Obviously, then you lose those cutouts from the shadows, but for our use cases, it wasn't really noticeable and it wasn't worth the trade. And second, we moved towards modeling leaves fully rather than using alpha cutouts. So if we have that leaf with the frond, rather than a larger poly with alpha cutouts, we'll model each of the fronds. Obviously, that uses more polys, but that doesn't matter as much now, and it's much quicker than having those alpha tests in there. So this is a definite example of performance testing in pre-production saving us in the long run. If we'd identified that late and had to go back and change many assets, all of the plants in our game, it would have been much more costly than early identification of how to build the assets and how to work well with the technology we're using. Which really nicely brings me to the last of my three questions. How do we get the best out of the technology we have? Let's have a look at some of the real strengths of Unreal 5 that you guys should be playing into. Static, high detail geometry. We can use much higher detail geometry than previous generations, and much higher detail geometry than users of other engines as well, because we've got Nanite and it's great. And we get the detail where we need it. Static lights. When lights are static, they're cheap. Even shadow casters can be reasonable. If the geometry they're casting on is static, the VSM will cache the shadows and the cost will go way down. Allowing a single light source to fill a space with lumen global illumination. We can think about lighting a bit differently now. Lights can bounce, they can bleed around edges, and they can really fill a space. Amazing looking characters with streamlined creation. That isn't particularly performance related, but I wanted to put it here. It's certainly something you should consider in terms of getting the most out of your tech. MetaHuman puts you ahead of the crowd right now. We're ahead of users of other engines with this tech. And that especially goes for you smaller studios. The tool set you have for character creation, sorry, I lost the plot. The tool set you have enables a smaller team to create results that a much larger team would be jealous of using a much more less advanced tech stack. So similarly, workflows enabling all disciplines. Unreal enables art, design, and other disciplines to get on and work without always needing code. If you only worked on Unreal, you may not realize just how huge this is compared to most in-house engines. We have tools and workflows in Unreal that we kind of take for granted that in-house engines can't dream of catching up with. They might catch up on one area, but there's such a wide spread on Unreal that it's very difficult for them. So this does have implications for budgeting and performance. The whole team is building and putting together the game with the tech they have, and therefore the whole team needs to be on board with performance. This isn't just a tech and code question. In fact, I'm going to take a huge left turn and talk about team dynamics there. Making games should be fun. More than that, I believe making games needs to be fun. Games are hugely complex pieces of software with fuzzy definitions like fun and satisfying. If you look at other industries, banking, websites, industry, whatever, the software they're creating is super simple by comparison to what we're doing. Maybe NASA writes some complex simulation software, fair enough, but even they don't have to have it run in real time, look photorealistic, have great accessible interfaces, but somehow we pull it off. And we make these amazing, complex, beautiful pieces of software. And a good proportion of the time, we manage to hit those elusive goals of fun and satisfying as well. And we do that because we love what we do. We love making games, and we look forward to coming to work in the morning. We make it happen. So to allow that magic to happen, we need a team to have each other's back and allow each other to enjoy the work. If we try to make games in an atmosphere of fear, many things go wrong. And sort of pulling myself back onto track, budgeting's one of them. You need whoever's making the budgets to be able to be positive, to be optimistic, and to know that if they overshoot, the team will have their back and deal with the consequences, even if they are quite significant, they might be. It's similar to time estimating. If you have that atmosphere of fear of consequences, your coder will tell you every task's a month because they fear overshooting. And your game performance budgets will also be overly cautious. Okay, back to the tech program. These things can be expensive. Moving shadows from lights moving or geometry. Might sound obvious, but if shadows are moving, they cannot cache. We've seen it's important. Moving shadow casting lights will always be expensive. Static ones, it depends what they're shining on. One additional thing to keep in mind while lighting an area, shadowed point lights and shadowed rec lights have additional shadow maps because they cast in all directions. So shadow costs are higher. Spotlights are cheaper here as they're only doing one shadow map. Try to keep the area your shadow casting lights are hitting as small as possible so you don't have too many lights affecting one thing moving through the scene at any one time. Moving foliage. If you have moving foliage or really any reason a hell of a lot of geometry is moving in your scene, we can see there's a load of additional costs both from Nanite and shadowing. Keep very tight control on the number of shadow casting lights if a lot is moving. And go and have a look at the excellent talks from Matt Osterley from last year and from earlier today on this subject. You need to have a look at your WPO distance checks to keep perf under control. And I suspect things are going to continually develop from Unreal here, maybe with more control around shadowing, etc. So I'll be watching keenly for more updates from Epic in this area. Oh yeah, check Matt out. He knows his stuff. Okay, hair strands. I wanted to talk a bit about hair. Unless you're lucky enough to be making a game about attractive, shiny-headed, bald gentlemen, it's something you're going to have to think about. Your characters are something that's always moving in your scene. So they'll continually need shadows calculating for any lights they're in. When you come to hair, you have a choice of strand or card-based hair. Our findings are that strand-based hair can get quite expensive for a current console title, and a big cost of that is shadowing. So if you have one light, it has a cost, but if you have multiple characters moving through multiple shadow casting lights, this really adds up to a big cost. When you look at that trade-off on the current console hardware, really dig into what strand-based means for you in terms of limits it might put on lighting for your team. Strand LODs do work well for distance, but you may decide you need card-based fallbacks, or for many games at this stage, I think the trade-off might not be worth it, and cards may still be the way forward for this console generation. And wrapping up there with alpha, we've discussed it earlier. It can be better to model detail right now rather than using those alpha cutouts. Okay. Right, I'm nearly wrapping up. We can nearly get to the mixer. Let's try and bring this to a conclusion. Testing in context is greater than single number budgets. We've talked about testing context with representative assets and using those numbers to work out what you can run. You may decide still to have some single number GPU budgets, like maximum this for VFX, or the Nanite-based cabas can never run over this one. But I don't think of them the same way as I thought of budgets before. They're more of an absolute maximum that could ever happen, because context is still so important. There may be a certain scene where you need that pass to be running way lower than the maximum that you've put in the budget, because you're leaning into something else and your budget is going somewhere else, so you need that budget to be lower. So they can be useful maximum caps to flag something's gone horribly wrong, but they're not the kind of key way to work out how your scene fits together anymore. Answer the 3 questions. What features should we choose for our game? How do we know what we're building will run? And how do we get the best out of the technology we have? Start testing, keep testing, auto-testing. Can't say enough about testing. Set tests up early in pre-production and keep testing as you develop. With the best will in the world, some of the presumptions you make are going to turn out to be wrong and will need updating as you go. But having that initial finger in the air is far better than not. Auto tests are amazing for tracking performance as you go and knowing if you lost performance, exactly when it happened and why it happened. I highly recommend you get them running. Create simple rules from your complex tests if you can. The forms those rules might take is very dependent on your team and your game. But as an example, we're looking at rules around the number of characters and the number of lights affecting them at any one time, e.g., in this type of environment design, you can have X characters on screen minus Y for every additional shadow casting light you're hitting them with. The rules are going to be different between somewhere with moving foliage versus a more static interior scene. Again, you may still decide to have some rules around GPU, but always be aware of context. Look at where you're focused and where to spend the budgets. There are many ways to get great performance out of Unreal 5. For instance, shadow casting lights are not always expensive as long as the shadows are getting cached. You can look at this either for your whole game or per scene in your game and say, well, here we're really showing off the lighting, so let's keep everything a bit static and a bit simpler. Or in this scene, oh, it's a storm, so everything's moving. Let's go to town on that and have everything moving, but let's keep the lighting really simple and perhaps the draw distances down here. Okay, that's about it for my slides. A couple of reminders. Make sure to keep the whole team in the loop on decisions. Make sure to test in final lighting and final environments and worst case lighting. And have fun. Thank you.